So we begin with derivative notation. In our previous section, we were working with the limit definition of the derivative, and we introduced the f prime of x notation. But if the function is defined as y, then its derivative would be y prime, or we can refer to it as dy dx. So y prime is the same as dy dx. Or instead of f prime, we can say that f prime of x is the same as d dx of f of x. So these are all equivalent forms of the notation of the derivative, and if you see any of them, it means to find the derivative of the function given to you. So we begin with the discussion regarding a constant function, and the question says, what is the slope of a constant function? So we should remember that y equal to a constant is a horizontal line. So this graph here is a constant function, and we're asked to recall slope of the constant function. So constant function has slope equal to 0. And we're asked to recall slope because derivative is the rate of change of a function, and rate of change is synonymous with slope. So when we talk about derivatives and slope and rate of change, they are all similar because we can see the slope or the rate of change of this constant function is 0. It is not increasing or decreasing as x changes. So we're talking about how does y change as x changes. Delta y over delta x is slope. And if we look at dy over dx, which was our derivative notation, which is the same as f prime of x, we're talking about a rate of change of a function. It is the same concept as slope. So we can say the derivative of any constant will be 0. Next, we have the power rule, and the power rule comes from seeing pattern recognition with the limit definition of a derivative. So we can recall that f prime of x was equal to the limit as h approaches 0 for f of x plus h, subtract f of x all over h, and if we were to have f of x equal to x cubed, the limit definition would give us f prime of x equal to 3x squared. With this, we can say, notice the 3 in the exponent becomes the coefficient here. And notice the exponent is reduced by 1. Well, that is exactly what they're telling us. If f of x is x to the nth power, notice the n comes out front, and the exponent gets reduced by 1. So let's just go through a couple of different examples. 2x to the 4th would equal a derivative of 8x to the 3rd, because we would take that 4 and multiply it out in front. So 4 times 2 is 8. That gets us our new coefficient, and then we subtract 1 from the exponent, and we get 3. Suppose I defined a function h of x equal to 1/2 x to the 6th. Can you calculate h prime of x using the power rule? You should take the exponent of 6, multiply it to the coefficient, so 1/2 times 6 is 3, and then you should reduce the exponent by 1, and you should get 3x to the 5th. But suppose I have a function p of x equal to the square root of x. We had solved this using the limit definition for derivatives also, but now can we use the power rule? We can start by saying, let's rewrite p of x as x to the 1/2 power. because the 1/2 power is the same as the square root of x. Then the derivative p prime of x, we would take 1/2 and multiply it by the coefficient. That would give us 1/2 x. And when you subtract 1 from 1/2, you get negative 1/2 in the exponent. And this is correct, but the answer might be expressed in a different way. So we can say, or p prime of x, negative means it goes in the denominator, and 1/2 means it's a square root. So we can say, could be expressed as 1 over 2 square root of x in the denominator. They are equivalent answers. Let's continue practicing this with some other examples. Suppose I had a function r of x equal to 1 over x squared. Then I should rewrite r of x as x to the negative 2 power, because a negative means reciprocal when it's in the exponent, and we've taken the reciprocal of 1 over x squared and written it as we've taken the reciprocal of 1 over x squared and we've rewritten it as x to the negative 2 power. Now we can use the power rule. So to find the derivative of r of x, we would say r prime of x equals, and we're going to take that exponent and multiply it out front. So that gives us a negative 2x. Now we want to subtract 1. Negative 2 minus 1 is negative 3. So r prime of x will give us negative 2x to the negative 3rd power, or we can write r prime of x as negative 2 over x cubed if we make the exponent positive again, using the reciprocal rule. So these are all techniques we can use the power rule for. We see that we used it for x to the n, we used it for nth root of x, and we used it for 1 over x to the n. These second two require a rewrite. So that we can express it in x to the n format. If we're ever unsure if the power rule applies to the derivative that we're evaluating, we can always check our work using the limit definition that we learned in the last section. So you can do this example on your own. What do you get for f prime of x? Hopefully you say 5x to the 4th. How would you find f prime of x if f of x were equal to the cubed root of x? Well, first we want to rewrite f of x. So if the square root was the 1/2 power, the cubed root will be the 1/3 power. Now we can evaluate the derivative. So evaluate f prime of x using the power rule. And we see that f prime of x is equal to 1/3 x. When you subtract 1 from 1/3, you get negative 2/3. Or you can express f prime of x, because it's a negative exponent, we can put it in the denominator, 1 over 3 times, remember 1/3 was the cubed root, so we still have a cubed root, but we also have a numerator, which is the square. And the negative has been removed because we have rewritten the expression in the denominator. So once again, these two expressions are equivalent. Next, we have the multiplication property for derivatives, and this basically states that if we recognize a constant multiplier for a function, we can pull that constant multiplier out front and reapply it after the derivative. So an example would be that if f of x were equal to 4x to the fifth power, we can say that f prime of x is equal to 4 times d dx of x to the fifth power. So I'm using that other notation. D dx means evaluate the derivative. And what is the derivative of x to the fifth? You should get 5x to the fourth, but you still have this 4 out front. So 4 times 5x to the fourth gives us an f prime value of 20x to the fourth. And again, with polynomials, I can just say multiply 5 by 4 and get 20, and then subtract 1 from the exponent, and we see we have the same answer here without breaking it down into all of the forms. But this is useful for when you're dealing with a function that you're not familiar with, if it were not a polynomial function, or if it were not a rational function. And we can then say, let's take the constant multiplier out, evaluate the derivative, and multiply it back in afterwards to get the same answer. And the sum and difference property states that we can take the individual terms of a function and differentiate them on a term-by-term basis, and then add their results together in the end. So notice we have u to the x and u prime to the x. We have v to the x and v prime of x. These are terms of f of x. And here's using our other notation. We can say y prime equals u prime, and depending if it's a plus or minus, you have and here we're using some other notation that we were introduced to at the beginning of this lesson. So if we were to find y equals u plus or minus v, then y prime would be u prime plus or minus v prime. Or dy dx, this is the same as y prime, is equal to du dx, this is the same as u prime, plus dv dx, this is the same as v prime. And there's multiple notations because different mathematicians were contributing to the derivative at the same time, so both of their notations were adopted, and it becomes useful, both notations. Often I like to use the d dx notation when dealing with implicit derivatives. We'll get to that in a later section, but it helps keep the work organized in terms of implicit derivatives, and I like to use function notation in terms of explicit derivatives. So here's an example with a fraction, and we can rewrite this fraction so that we can address it on a term-by-term basis. So rewrite f of x equal to, and basically this x to the fourth is dividing each term in the fraction. So we can write it as 1 over x to the fourth plus x squared over x to the fourth. And you should see that you can easily reverse this. When the two denominators are matching, like denominators, we can combine the numerators and we get back this fraction. So we've just reversed that process of combining fractions with like denominators. So now that we've split it up, we can take these derivatives independently. Differentiate on a term-by-term basis. So f prime of x will equal d dx. And I'm going to write 1 over x to the fourth as x to the negative fourth plus d dx. I see that this fraction simplifies. X squared over x to the fourth is 1 over x squared. So I can rewrite that as x to the negative 2 power. Now we see that our f prime of x, if we take the first derivative, or the derivative of the first term, I should say, this gives us negative 4 times x, and if you subtract 1 from negative 4, you get negative 5, plus, and now the next term, when we multiply the coefficient by the exponent, we get negative 2 times x, and when you subtract 1 from negative 2, you get negative 3. And f prime of x is equal to negative 4 over x to the fifth, and the plus negative 2 becomes minus 2 over x to the third. And this is correct, and it could be rewritten algebraically if we find like terms for the denominator to combine it. So this is also correct. And you see that we get multiple versions for our answers based on the algebra we want to use to rewrite it or to express it in different forms. So here's another problem down at the bottom for you. Pause the video here. You can work this one out on your own. Remember, we can split up the fraction and then evaluate it on a term-by-term basis. So try that now here, and then unpause when you want to check your work. So we will begin by rewriting f of x as 5 over x minus 3x over x plus 4x squared over x. And now I can rewrite this again, saying that it's 5x to the negative 1 for the first term, so I can use the power rule. For the second term, I see that the x's cancel out, so I can write it simply as negative 3. And for the third term, I see the denominator x cancels with the numerator x, leaving just 4x. And now f prime is the derivative of each term, so we're going to multiply the exponent by the coefficient. That gives us negative 5x. And when you have negative 1 in the exponent and you subtract 1 more, that puts you at negative 2. And now we can say, what's the derivative of any constant? What's the slope of a horizontal line? And that would be 0. And this third term has a 1 as the exponent. So 4 times 1 would give us 4x. And when you subtract 1 from 1, that gives you x to the 0 power. And anything to the 0 power is 1. So 4 times x to the 0 is the same as 4 times 1. So this last term reduces to 4. And we can simplify our f prime by saying this is negative 5 over x squared. The 0 I don't need to write, plus 4. Or I can get a common denominator and say that f prime of x is equal to 4x squared minus 5 all over x squared. And that's just an algebraic rewrite by getting like denominators and combining. So for example 5, they gave us a polynomial. We just have to take the derivative on a term-by-term basis. There's no radicals, there's no fractions, there's no negative exponents. So it's just 5 times 3 gives us 15. X, subtract 1 from the exponent, and we're at 15x to the fourth, plus 4 is the exponent, so we get 4x to the third, minus 3 times 2 gives us 6x to the second, plus 2 times 5 gives us 10x to the first, minus 7x to the 0, which is just minus 7, and then the derivative of a constant is 0, so that disappears, and we see that we rapidly generated this derivative function. This should say f prime of x here, and this is much more efficient than using that limit definition for derivatives, but we still refer to it when we are working with unfamiliar functions and evaluating those functions' derivatives for the first time. So here are some textbook exercises that implement the properties of derivatives. And if we look at this, we see it says refer to the functions of g and f that satisfy f prime of 2 equal to 3 and g prime of 2 equal to -1. And in each problem, we are asked to find h prime of 2 for the indicated function. So if we look at number 27, they're telling us that h of x is equal to 4 times f of x. And if we take the derivative of h of x, anything you do to one side of an equation, you have to do the same thing to the other side of an equation. That's familiar to us from algebra. And now we can use that constant property. We can say, well, let's take this constant 4 and we'll put it out in front. So d dx of h of x is equal to 4 times the derivative of f of x. And I can replace this d dx of h of x and just call it h prime of x equals, and I have a 4, and I can replace this d dx of f of x with f prime of x. So we didn't really have to do all of this work, just applying the properties exactly the way they were presented to us, but we can then start to just go right to this part of the answer. So we are asked to evaluate h prime of 2. So that means we'll get 4 times f prime of 2. If I replace x in the h prime with 2, then I have to replace all x's with 2. And we see that f prime of 2 is 3 up in the directions. So this means that h prime of 2 will be equal to 4 times 3, because we replaced this with 3, because that was given to us. And we can finally say that h prime of 2 is equal to 12. And that is problem 27. That just applied the multiplication property for derivatives. Let's do this again for number 29. So number 29 tells us that h of x is now defined as f of x plus g of x. And if we evaluate h prime of x, that means we're taking the derivative of each term inside of h of x. So therefore, we have h prime of x is equal to f prime of x plus g prime of x. And once again, we're asked to evaluate h prime of 2. And since I replaced the x with 2 in h prime, I have to replace all x's with 2. And this means that h prime of 2 is equal to, well, we want to look up what is f prime of 2. F prime of 2 is 3. So we'll plug in that 3 here. What is g prime of 2? We see g prime of 2 is negative 1. So we'll plug in this negative 1 here. And we can say that h prime of 2 is equal to 2 now. Let's look at this again for problem 31, where h of x is defined as 2 times f of x minus 3 times g of x plus 7. So if we are going to evaluate h prime of x, we're going to use the multiplier rule and say that this is the same as 2 times f prime of x minus, again we have a multiplier, 3 times g prime of x, and the derivative of a constant is 0. So I don't need to represent that term at all. Now we are asked to evaluate h prime of 2. Now we are asked to evaluate h prime of 2. So that would give us 2 times f prime of 2 minus 3 times g prime of 2. And we would go back up to the directions and get the values for f prime of 2 and g prime of 2 and plug them in. So 2 times f prime of 2 is 3, minus 3 times g prime of 2 is negative 1, and this gives us 6 plus 3. This gives us h prime of 2 equals 9. So we have some applications in this chapter we would like to apply derivatives to, and that is instantaneous velocity and finding the slope of a tangent line at a point on a curve. So here is our instantaneous velocity problem. It states that an object moves along the y-axis marked in feet so that its position at time x, which is measured in seconds, is modeled by this function f of x. Part A says find the instantaneous velocity function. So part A. Velocity as a function of x is equal to 3x squared minus 12x plus 9. Velocity is equal to f prime of x. And we see that f prime of x is a polynomial, so we can evaluate the derivative term by term. And velocity is the rate of change in distance as time changes. So that's why once you hear rate of change, once you can express something as rate of change, we're talking about derivatives. Part B says find the velocity at x equals 2 and at x equals 5. So we want v of 2. So you're going to plug in 2 for all the x values. That gives us 2 squared, which is 4, times 3, which is 12, minus 12 times 2, which is 24. So that's 12 minus 24 is negative 12. Negative 12 plus 9 is negative 3. And because this is measured in feet and seconds, it is negative 3 feet per second. That is the rate of change in distance, and distance is measured in feet, over the rate of change in time, and time is being measured in seconds. So we can do this again for x equal to 5. And for part B, we say v of 5 is equal to 3 times 5 squared minus 12 times 5 plus 9. V of 5 is equal to 75 minus 60 is 15, plus 9 is 24, and this is measured in feet per second. Part C says find the time or times when the velocity is 0. Well, we know velocity is 3x squared minus 12x plus 9, and we set this equal to 0 and solve for x. So we'll start by factoring. This gives us 3x minus 9 times x minus 1 equals 0. And we take each factor and set each factor equal to 0. So we have x equals 3 seconds. We have x equal to 1 second. And if you plug in either of these values into our velocity function, then we should end up with 0. So let's try it. 3. If I plug in 3, I get 3 squared is 9, times 3 is 27, and 12 times 3 is 36. So 27 minus 36 is negative 9, plus 9 will give us 0. So that is one location where the tangent line is horizontal. And if we plug in 1, we get 3 minus 12 plus 9, which gives us 0. So those two answers give us the locations where the tangent line is horizontal, meaning the velocity is 0. Here we have a question asking that we write the equation of a tangent line. They gave us a function, and now we have to find its derivative, because the derivative calculates the slope of a tangent line. Derivative is used to measure rate of change. Therefore, it finds the slope of the tangent line. So first is the derivative. F prime of x is equal to 4x cubed minus 12x plus 0. Part B says find the equation of the tangent line at x equals 1. So slope of tangent line at x equals 1 is f prime of 1, which equals 4 minus 12, which is negative 8. So this is the slope, which we use the letter m for, and for tangent, so in subscript, I write m tan, which is negative 8. But now we need to use this point to find the y value that goes with it. Find y value of original function. So f of 1, not f prime of 1, but f of 1. If we come up here, we would get 1 minus 6, which is negative 5, plus 10, which is positive 5. So that gives us an ordered pair of 1, 5, and that ordered pair is our tangent point. Part C says find the values of x where the tangent line is horizontal. Okay, so to finish part B, we need to find the equation of the tangent line. So now that we have slope and a point, we can use the slope point formula. So y minus y1 equals m times x minus x1. The known point is our x1, y1, and our slope goes in for m. So this gives us y minus 5 equals negative 8 times x minus 5. This gives us y minus 5 equals negative 8 times x minus 1. And this gives us y minus 5 equals negative 8x plus 8 after I use distributive property. And finally, I can say y equals negative 8x plus 13. And this is the equation of our tangent line at the point 1,5. And if they change the x value we're working at, we get a completely different tangent line because the slope will change and the given point will change. Part C asks that we find the values of x where the tangent line is horizontal. So we have our tangent line, but we want to know when the slope is horizontal. That means look at the derivative and set it equal to 0 to answer part C. So we can factor out a 4x, and that leaves us with 4x times x squared minus 3, and we set each of the factors equal to 0. So we get x equals 0 and x equals plus or minus the square root of 3. And that's your answers to part C. Those are the x values that will give us a tangent line that is horizontal. This is the end of this presentation. So watch the video, take your notes, complete the practice, and come to class with questions.